As we did for capacitors, we're going to look at what happens with networks of resistors. And so we'll continue to do the same kind of thing we did with capacitors when they were in series and parallel, replace them with equivalent resistors, and also talk about what's the same and what's not the same for resistors that are in series and in parallel. So first, when we have resistors in series, what we mean by that is that the current is going to be the same. The current really has only one way to go, and that's through the two resistors that are in series. So the current is the same. So the voltage across the resistors can be different, and the equivalent resistance is just the sum of all the resistors that are in series. When they're in parallel, just like with capacitors, of course, the change in voltage, the voltage drop, is the same. So we still have energy conserved, and the equivalent resistance for in parallel is this inverse relationship. 1 over R1 plus 1 over R2 plus however many are in parallel, all raised to the minus 1. So we're going to see how we can do this with an example that we've got right here. So what I've set up is a battery and some resistors. And to start off with, none of them look like they're really all in parallel or in series with each other. So we sort of have to, again, like the capacitor, we have to sort of say where is a piece that we know what's going on. And the first piece we can say something about is if we look at this point right here and this point right here, we realize that R4 and R5 share the same top and bottom part, these two orange parts, and that means the voltage across R4 and the voltage across R5 have to be the same, because if we walked around this circuit through R5 and then back through R4, it would be like we would come down and then go back up to the same place. And so these are in parallel. So we can replace them with their equivalent. So we can redraw this. R1, and we've got R3, and we have R2, and then we have what I would replace it with, this R3 parallel R4, this parallel equivalent, okay? So that equivalent resistance there. And then once we have that, we can recognize, hey, the current that goes through R3 must go through this equivalent resistance. And so we can replace that. R1, R2, and then we have this one, which we'll call this this is 4, 5. We'll call this R3, 4, 5, where R3 is added to this parallel combination of R5, because when they're in parallel, we have this 1 over relationship. When they're in series, they just add, so that would be the equivalent. So R3, 4, 5 is just going to be R3 plus this equivalent resistance. And then we can recognize that these two are now in parallel because they share the same top and bottom connection. And so we can replace that with, here's R1, an equivalent resistance here, where this would be R2 in parallel with R3, 4, 5. And then finally, these are all in series. So we're going to find the values and then work on the kinds of things we might ask. So the kinds of questions that we might have for something like this, a problem that we might be asked to find would be find the current total out of the battery, the power. We could find the current through each resistor. We could find the voltage drop across each resistor. So all of those, or the power heating up, the thermal energy coming off of each of those. So those are all questions we could answer. And so we're just going to do a general, how much information can we get, and let's make sure that it's all consistent. So as we have R4 in parallel with R5, 4 in parallel with R5, that equivalent resistance is equal to 1 over R4, which is 4 kiloohms, plus 1 over 5 kiloohms. And you can write this all as kilo, or you can realize by the time we invert it again, we're going to be back to kiloohms. So I tend to do this in the following way. I tend to do this as 1 over 4 plus 1 over 5, all to the minus 1, and we're going to be left with kiloohms out there. Okay, so once we've done that, 1 over 4 plus 1 over 5, when I calculate that, this gives me then 2.2 kiloohms. So that is 2.2 kiloohms is my resistance. So R3, so I again did the same kind of thing I did in the previous example so I can keep track of the numbers. 3 is going to be 3 kiloohms. So R345 is just going to be 3 plus this 2.2. So 3 kiloohms plus 2.2 kiloohms, or 5.2 kiloohms. So this is 5.2 kiloohms. And then the parallel group, this is going to be 1 over 2 plus 1 over 5.2 to the minus 1 kiloohms. And that I get to be 1.44 kiloohms. This is 1.44 kiloohms. This one was 1 kiloohms, and let's see, my battery was, in this example, 12 volts. Okay, so 12 volt battery, 12 volt battery. Okay, so having done this, we can find the current through the battery, because now we finally got that we have 12 volts, and our equivalent resistance of the whole group of resistors is 2.44 kiloohms. So the current total coming out of the battery and going through, right, it comes up into the battery, leaves the battery. That's the current, because current in equals current out. So I total, using V equals IR, which we will use over and over again. So V equals IR. Remember, this is really a delta V, your change in voltage, but in shorthand we usually write it as V equals IR because we think of this as being at 0 volts, so this point right here would be at 12 volts. And our notation for 0 volts often is we say 0 volts is the ground, so often you'll see it like this, where this symbol means ground. Earth ground sometimes. So you'll see it like that. You'll sometimes see this signal like this on circuits. That means an earth ground. Means it's connected to the earth, which is a source or a sink of electrons. So we can think of that at 0 volts. And we're generally at 0 volts because we're connected to the earth. Okay, so our current, after that little digression, using V equals IR, our current is voltage over R, 12 volts over 2.44 kiloohms. 12 divided by 2.44 is equal to 4.91. So 1 over kilo, 1 over kilo means 10 to the third. So 1 over 10 to the third is 10 to the minus 3, or which is, of course, milli. So this would be milliamps. So if I have kiloohms, then I end up in milliamps. And so I just use them instead of putting all the extra zeros in. That just is easier to work with. All right, so our current is now 4.9 milliamps. So that is the current coming out of here, 4.91 milliamps. So that's the current going through this resistor and through this resistor. So now we can find the voltage through each of those. So V1 is just going to be I times R1, which is easy. So that's 4.91 volts because I've got milliamps times kiloohms, so that gives me volts. So that's the voltage for 1. For this second one, I'm going to get rid of this work now. we can say, again, V is equal to IR. And so the current is still 4.91 milliamps. The resistance is 1.44 kiloohms. So the voltage there, if I multiply those two together, I get 7.07 volts. So we can check this value because the voltage across this is 7.07 and the voltage across this is 4.91 volts. So if we add those two together, 4.91, so 4.91 volts plus 7.07 volts, that gives me 11.98 volts, which is supposed to be 12, so our rounding would give us actually 12. If we were a little more careful, if we'd kept another decimal point in the milliamps, then we could get that all to match up. But that should equal 12 volts. Okay, so that's a good way to check. And in fact, we could have used that to find the voltage here instead of using I times R. Okay, so moving back into the circuit, we're sort of unpacking the circuit. We found this equivalent resistance, so I need this space back. And so now we know that the current here is 4.91 milliamps. We know the voltage here is 4.91 volts. And then we know the voltage across these two resistors. So this is 2K and this one is 5.2K. We know that the voltage across here, plus minus, is 7.07 volts, 7.07 volts. And so now we can find the current in each of these sections, right? The current through R2 and the current through this 3, 4, 5 equivalent. So the voltage for 2 is equal to the current for 2 R2. So we've got 7.07 volts is equal to I2 times 2 kiloohms. So the current is going to be in milliamps. 7 divided by 2, so about 3, actually 3.45 milliamps, right? So that's the current here. So that is 3.45 milliamps. And then we can find the current for the 345. So voltage across 345 is 7 volts. Current through the 345 times 5.2 kiloohms. That's 7.07 volts. And so that gives us a current through this equivalent resistance of 1.36 milliamps. So that says that our current right here is 1.36 milliamps. And we can check because the current in is 4.91. So if we add these two, 4.91 should be 3.45 plus 1.36. And if I add those together, I get a 1, I get an 8, and a 4. So I get 4.8 or thereabouts. Oh, sorry, this is not 3.45. My mistake. 5.4. I didn't write it correctly. There we go. Okay, so I get basically a 4.9 milliamps. So that's correct. So that all matches up. Because this current plus this current equals that current. Okay, so we'll carry this on. So just rewriting this, again, we got 4.91 milliamps. We got 4.91 volts across here because it's a 1 kiloohm. This we have 3.54 milliamps, and we have a voltage here of 7.07 volts. R3, we have 1.36 milliamps going through here and 1.36 milliamps going through this equivalent resistance, the same current that we have right down here. It's going through this equivalent circuit. And so then we can find the voltage that each of these has. The voltage across R3 and this parallel group of 4 and 5 had better equal my 7.07. So the voltage across here and here needs to equal 7.07. So we'll check that. So the voltage across 3 is I times R3. So voltage 3 is equal to 1.36 milliamps times 3 kiloohms. So voltage 3 is equal to 4.08 volts. So that gives me 4.08. And then voltage across 4,5 is equal to the current times the effective resistance of 4,5. And so that is equal to 1.36 milliamps times 2.2 kiloohms. So the voltage across 4 and 5, each of them, is 2.99 volts. So this one has 2.99 volts. So let's make sure. 2.99 volts, 2.99 volts plus 4.08. We can check. That gives us a 7, carry the 1. So that gives us 707. So that is all consistent. Okay. So now we're basically done. This gets to be kind of a messy setup. I'm just going to draw the currents in, 4.91 milliamps. This one is 3.54 milliamps. This is 1.36 milliamps. Then to find the current in R4 and R5, because this 1.36 splits into two branches, then we need to say what is the voltage across each one, and then from there we can find the current. So we know the voltage across R5 and R4, this delta V, is equal to 2.99 volts, right, across R5 and R4. So the current for 5 using V equals IR. So V equals IR. So I is V over R. So we get 2.99 volts over 5 kiloohms. So the current through 5 is 0.598 milliamps. And the current through 4 is 2.99 volts over 4 kiloohms, which is equal to 0.748 milliamps. When we add those together, we get basically this 1.36 or thereabouts. I've got extra significant figures now, but that gives you the same. These two currents add together. This is basically 0.60 and this is 0.75, and when we add those together we get 1.35, which is basically the 1.36. Okay, that's milliamps is the current. And so from that we get the voltage across every set of resistors. That's in this diagram here where we figured out the 2.99, 4.08 across the R3, that's volts, and the voltage across all of them. I didn't calculate the power. You can find the power by using any of the expressions that we have, right? Power is equal to V times I, or substituting in for V IR, this becomes I squared R, or if you want to, you can substitute in for I, V over R, so then you get V squared over R. Any of these relationships work. Just as an example, we can say the total power from this battery is just going to be V times R, so the power delivered by the battery, from the battery, is equal to V times I, which would be 12 volts times 4.91 milliamps. So we got to keep that milli. And so when we multiply this out, I get 58.9 milliwatts, watts, because volts times amps. So that would be 0.059 or thereabouts watts of power, which is fine. It's not very much power. Just for reference, the very smallest resistors that you had in class, so when you had the little resistors with the codes right on them, I know they were colored codes, those were, the smallest ones were 1/4 watt resistors. The next size up is about a 1/2 watt. I think you have 1 watt resistors. And then the big, you saw also in class some sort of bigger square ones that were white, right? And they were, these were 25 watt resistors. Okay, so this is an easy circuit to build because 1/4 watt resistors are very common and very inexpensive. 25 watt resistors are more expensive because they need to be able to not melt. And what happens to these 1/4 watt resistors, if you put too much current through them, you have too much voltage which generates too much current, is you do actually burn them up. They tend to fry and smoke. And then we put them on the wall as showing that, hey, we burned a resistor today. But I haven't set off a smoke detector yet in the building, so that's good. I've just set little tiny fires with these resistors. I'm sorry we don't get the opportunity to do that kind of thing. We don't do it on purpose, of course, but that is something that happens when you short things out or you put too much current in something. That is why people worry about electrical fires. With like a 25 watt resistor, the thing that tends to cause electrical fires and things like that is if you have too much current, but also you have a carbon track where you've got a path where on a resistor of carbon where the current can go, and that's lower resistance, and then that tends to burn up. So that's where you get dangerous situations in, for example, household wires.